Hi, my name is Jack Ferris, and for this design project I focused on the problem definition and design comparison between a four-wheel and a six-wheel rover. To start with, my role was clearly defined with what the engineering problem actually was. The main challenge, the main challenges that we were given were to design a rover that could traverse uneven and challenging terrain, while staying stable, carrying a 400-gram load, and remaining within the strict constraints that we were given. These strict constraints included an A4 footprint, a €100 budget, it could only be powered by DC, and it was a requirement to safely navigate all obstacles such as the slope, the rock crawl, a pipe bridge, and water. Defining these limits early was really important because they guided every design decision we made later in the project. It also made it possible to ensure that any changes made to the rover wouldn't hinder the design compliance to constraints. Once the problem was clearly defined, I moved on to comparing two possible rover configurations, both a six-wheel and a four-wheel design. The goal here was to determine which option would perform better across all obstacles, rather than just one or two. I analysed how both designs would behave on each obstacle. I discovered that the four-wheel design performed reasonably well on flat surfaces and gentle slopes, but it struggled more with complex terrain, especially the rock crawl and water obstacles. To perform well in those environments, the four-wheeled rover would require a suspension system, which adds a lot of complexity, cost, and a risk of failure. Whereas on the other hand, the six-wheel rocker bogie design, it maintains continuous ground contact throughout the run, so it allows the rover to remain stable without needing springs or any complex suspension systems. This is a major advantage. The rocker bogie system also distributes weight more evenly across the wheels, improving traction and obstacle crossing ability, particularly on uneven surfaces. As part of the comparison, I carried out background research on the six-wheel design, which I gathered researches on YouTube videos and technical explanations, which we compiled into the OneNote, and I looked at why the NASA uses rocker bogie systems rather than four-wheel designs on their Mars rover. This research reinforced our findings, showing that the six-wheel design is preferred in environments where reliability, stability, and adaptability are critical. Another important part of my contribution was ensuring that all design decisions stayed aligned with project requirements. As the design changed over time, I checked that changes didn't push us over budget, exceed the maximum dimensions, or negatively affect the rover's ability to complete any of the obstacles. This helped support the final decision to move forward with the six-wheel rocker bogie system. This became the foundation for the rover's mechanical layout. So overall, my contribution helped establish why the rocker bogies design was a more suitable solution for this project. By defining the problem clearly, comparing designs, and supporting my decision with research and constraints, I helped the team towards a design that was stable, practical, and achievable, and within the project limits. Thank you.
Hi, my name is Matthew Shaw, and the part of the project I was focusing on was the dimensioning of the rover and tracks. So, first, accurate sketches with critical dimensions were created for the tracks so that all team members can understand the obstacles that the rover must cross. The dimensions of the rover will also depend heavily on the dimensions of these tracks. So, for the side slope, it was measured that the slope is 250 millimeters wide, and the grips from center to center are 190 millimeters. The angle of the side angle is 30 degrees, so this is not the angle the rover will have to climb, but this is the angle the rover will have to drive on without tipping over. Then for the pipe bridge, a sketch was also made that has a plan view, side view, and 3D view. The angle of the ramps measured to be 21 degrees, and the ramps are 250 millimeters wide. For the water trough, the ramps are 250 millimeters wide and the angle is 18 degrees, and the deepest the water could possibly be is 100 millimeters. For the V-gully, a plan view, side view, and 3D view were created. Um, the ramps are 400 millimeters wide and the slope is about 20 degrees. There's a slight turn in the middle of the V-gully. For the rock crawl, a plan view, side view, and 3D view were created. The ramps are 190 millimeters wide and the rocks itself are 230 mils wide. So then, based off these dimensions, sketches were created for the rover. A front view and a side view were created. Then these sketches could be used by Oshin, who's doing the SolidWorks, to create a prototype of the rover.
Hi, my name is Milash Charak and I'll be talking to you about my part in this project, which was the motor sizing and the eventual motor selection. Motor sizing is very important as it ensures the rover can operate safely under all expected conditions. The motors are evaluated using the worst case scenario. In our case, this was a 20-degree slope. When looking at the maximum wheel torque calculations, we assumed that the mass of the rover is approximately 2 kg and the frame is made out of aluminium. For these calculations, we also used a factor of safety of 1.5. This gave us a maximum torque in the worst case scenario of 0.0639 per wheel. Basically, now we have to look at finding a motor that has a stall torque above our maximum torque. If our maximum torque was higher than the stall torque for a certain motor, this would cause the rover to stall on the slope and roll back, which is something that we don't want to happen. So we found these motors on Amazon. They have a stall torque of 0.078 Newton meters, which is above the maximum torque. This shows that they are clearly sufficient for the given operation. There's a graph on the right hand side of the page which shows the comparison of the normal operation and the worst case scenario, also comparing that to the motor stall torque. So these are, even the worst case is much less than the motor stall torque, which also includes a factor of safety of 1.5, we can't forget. So it shows that these motors are sufficient. The sketch at the bottom right hand side of the page shows a proportional side view of the space rover. The arrows indicate the load acting on each wheel, which is very important for weight distribution. When looking at the bottom middle of the page, we can see the selected motor. These motors are soldered, which also will save us time towards the end of the project when we are building the actual rover and putting everything together. That is everything on my part of this project so far.
Hi, my name is Sean Brady and I will be discussing the bill of materials and the tire selection. Our bill of materials outlines all the essential components required to build the rover. An Arduino Uno and an Arduino Nano will act as the main control units for different tasks. For mobility, we have 6 motors paired with 2 motor drivers. This ensures the rover can move reliably across the challenging terrain. To maintain stable power distribution, a voltage regulator is also included. The bill of materials includes key sensors such as a temperature sensor, a tilt sensor, and an ultrasonic sensor. This will provide important environmental and positional data during operation. For communication and user feedback, we have a Bluetooth module for wireless connectivity and an LCD screen to display real-time information. Additionally, steel material is listed for the rover's structural frame, giving it strength and durability. Overall, this bill of materials that ensures that every critical component from control units and mobility parts, sensors and structural material is included. This ensures that we have all the parts needed to construct the rover. Next, I will discuss how the torque and friction affect our tyre choice. Looking at graph 1, you can see that as the slope becomes steeper, the torque required from the motor increases. Therefore, it is not enough for us to design for flat ground. We must ensure that the motors can handle the steep slopes and the tyres can support the motors. Graph 2 shows that as the gravitational force on each wheel increases, the minimum friction coefficient also increases. This essentially means that as the heavier the rover is, the more friction is needed to prevent sliding. Combining the information of the two, the steeper slopes demand more torque, and as the torque increases, this increases the need for traction. So tire choice means matching the rubber compound and tread pattern to the terrain. Deep treads work best on rough or wet surfaces, while softer compounds and bigger contact areas are better for smooth and dry ground.
Hi, I'm Ocean Andrews, and I focus on the SolidWorks of the project. I focus on the design of our rocker bogie system and the motion analysis simulation in SolidWorks. So first of all, I had to look at the requirements. So I had to fit into the A4 footprint limit, and um, so first of all, we decided to do the rocker bogie mechanism. So that meant we had one small arm and one larger arm, and we connected these together using a pin. So this pin was our pivot point, and that's how the rocker bogie mechanism worked from this pivot point. So it could crawl up and go up ramps, etc. And the two different sides were connected together using two larger bolts going across the whole thing, and these were cemented in, so these were fully stable. And then I designed a component shelf to store all the electrical components. And on top of this, we slid in a can holder to hold the can while it's going along each track, and hopefully for the can to stay on top of it at all times. And this is the drawing sheet here on the left with all the dimensions. So there's the 6 wheels and the 6 motors, and yeah. So then on to the motion analysis of it. So I learned a lot about this simulations in SolidWorks. So first of all, I got the rover assembly and put it into another assembly with the track part. So I tested on the pipe bridge track, and I mated the front views together, the side views together, and the top views together to get it in line so it would go along the track smoothly and go on the pipes essentially. Um, for this to happen, I set all the motors at 80 RPM and all going in the same direction towards the ramp. Then I set gravity going down in the Y direction just to make it as real as possible for the testing. And then I added in contacts. So in the photo, we can see the wheels are the blue. They're the first contact group. And then the other contact group is the pink, which is the track. So these are contacted together. And this just meant that the wheels would run along the track and not go off the course. So in this contact, I had to select the wheels as being rubber and the track as being steel, because that's what they are in real life. And then I floated the rocker bogie system so it could move, and removed any mates that were in the way, and ran the simulation, and it went along the ramp, and the rocker bogie mechanism worked, and the 80 RPM was enough in each motor to get it along the track. And under that is the motion analysis setup timeline, so that just shows all the motors and the gravity and the contact points going along the whole timeline and each second of it. And then below that, the very end, is all the tracks I designed on SolidWorks. So these were just given to me, the dimensions were given to me by a teammate that measured them. So we estimated each track and designed it up on SolidWorks so we could test. And yeah, that's basically it.
My name is Zach Bourne. I was in charge of electronics. The first step to do was to define what the system needs to do. So the system needs to control the rover using a Bluetooth controller, but also have the ability to be overridden by an ultrasonic sensor in case of a crash. So if the rover is driving into the side of the track and the sensor senses this, so there'll be a tolerance to say if it's within 3 centimeters or something like that, then it'll override our controller. It'll reverse and turn and attempt it at a different angle. It also must display surrounding information, including tilt, temperature, and distance to nearest object, so environmental data about the surroundings. It must display this on an LCD screen, and then I have a little flowchart. That isn't accurate now exactly, because since then we found out that it's supplied by a 12-volt barrel jack, but I'll cover that in a few moments. We were lucky because I had an Arduino starter kit at home, which included an LCD, a couple of Arduino Unos, wheels, motors, motor drivers. So a lot of the components we already had, so we could make a stab at this before having anything set in stone. Then went on to testing. I have some background in this sort of thing, so I started testing the screens with all the sensors. Because I had to, well, the main reason for testing was some of the parts had to be soldered, so I wanted to make sure that they fully worked and I didn't make any mistake in soldering them. So I'll have a video attached at the end of this PowerPoint showing the information from the sensor and how it works. These two circuits were made just at home using rechargeable batteries, and they were controlled by spaghetti code, just generated code. It's not representative of what our actual code will be, but I also used a voltage regulator so it wouldn't fry the Arduino. And I also figured out that I need to use a 3.3 volt signal for one of the pins on my Bluetooth module. So now we'll go on to the circuit. So the circuit starts with a barrel jack where 12 volts is supplied from the wall. That is fed into a motor driver, and the motor driver, well, obviously the ground's plugged in as well. The motor driver outputs 5 volts and will lead that to the rail of a breadboard. That rail of the breadboard powers the LCD, the ultrasonic sensor, the tilt sensor, which in our case is an accelerometer, and then also the temperature sensor, which we have as an L35 or LM35, whatever it's called. It also powers both Arduinos, so the Arduino Nano and the Arduino Uno. So the Arduino Nano, in our case, is in charge of the sensors on the screen, and our Uno is in charge of taking in the signal from the Bluetooth and outputting that information to the motor driver and then to the motors. So luckily we only have to use one motor driver as well, because all 3 of the wheels on one side are going to be moving at the same pace at all time, and all the wheels on the left hand side are going to be moving at the same pace at all time. What else do I need to talk about here within that? Yeah, so you can obviously see the controller. That might be the final controller we're using. It's just an app I chose, and it's also an old phone that I found at home, because it doesn't use you can't use an iPhone to control this, HC05 or HC06, whichever one it is, because it's a different method of transmission for Bluetooth. And then I also have my pin layout there, which is all the just digital pins for most of them. Some of them for the motor driver, 2 of them need PWM pins. And you can see there the way I have all the motors wired up in parallel. I also have a serial connection from Uno to Nano. So that means that I can access the information on the ultrasonic sensor for the Uno code without having to wire the ultrasonic sensor into the Uno itself. I think that's about it. I'll attach the video here, and if there's nothing else after the video, thanks for watching and hope you enjoyed our presentation. Work now where it shows degrees instead of pitch and roll. So let's see, obviously distance sensor still works, temperature sensor still works. I can't really get it to settle on 0 degrees, but that's because I'm using this weird joke to hold it. I'm sure we'll be able to calibrate it once we've actually built the rocker bogie design, but there you go. Tilting it all the way, tilt it the other way, tilt it the other way. There we go. Works perfectly. The only problem is still the Uno, not the Nano.